I'm Lissi, I'm not sure his familiar name, he's my supervisor, and these are the other two collaborators, Christopher Kinkintveld from Texas El Paso University, and Branislav Boshansky, who's currently in Denmark. And so I came here to ICHCAI conference. It's an international joint conference on artificial intelligence, which is held this year in Buenos Aires. So I was giving a similar talk, so it's like similar to that one. So I'm going to talk about the optimal network security hardening using attack graphs games. So security games are becoming more popular. So there, in security games, so what is actually a game? So normally the optimization usually considers just one side of a decision maker and asks what action is the best, but it doesn't model how the opponent or the other players will react to my actions. So, and game theory tries to extend this thinking. So for every action that I do, I also consider what my opponent would do and think, and he also may think or reason what I actually would do and react on it best response. And so this game theory is now well used, about 5 to 6 years. For example, this is like work of different university in LA. So they applied the game theoretical approach for deciding where should air marshals, in what planes should air marshals be present, and watch, so no hitchhike would happen in that plane. So previously the air marshals, they were deciding on some strategy, but game theory apparently works better. Or for example, in LAX airport, the international airport in Los Angeles. So they also using game theory find out the best schedules, how the police or the police with the cannon patrols should go around, or where they should check whether there are some drugs and so on. So let me tell you more about the game theory. So I usually don't say this version because I speak to game theorists. So game theory can be, this is a simple one-shot game where two players play simultaneously, and so it can be considered that I'm a policeman and I can choose whether I want to do an action A. So A could be, for example, to protect Terminal 1, and B could be action to protect Terminal 2. An attacker could either attack Terminal A or attack Terminal B. So if I as a police would protect Terminal A, and attacker would attack Terminal A, so this is outcome of the game. So this is my utility, the first value is my utility, and second value is the utility of the attacker. So for example, if I protect Terminal A and attacker attacks Terminal B, so I will get -1 because Terminal B was attacked successfully, I didn't protect it, and attacker would gain 2 points for attacking that terminal. And so in this case, actually, it can happen that the attacker can observe the actions of the police by long-term surveillance. So he would watch us for a month or two, what we are doing, and so if we protect only A, so defender will attack definitely B. If we protect only B, attacker would attack A to get this outcome. So there is no best way how we can protect only one terminal deterministically. So best what we can do is to randomize to protect maybe this half of the time and this half of the time. So then the attacker doesn't have best response what to attack, A or B, but has also randomize his action, and then we only can gain by this. So this is one of the simple games, and that's how game theory reasons and tries to find some stable points called Nash equilibrium of the actions. And so my work is applying game theory and network security. And in my case, I assume that there is a defender who can apply honeypots into the network. So he has a set of honeypots, and he can put those into the network. And then attacker, he chooses what attack policy he wants to use in order to attack network. So this is so far our initial work. It's quite simple game. Okay, so first of all, what we do, network consists of several set of hosts, and each host we define by its connection to the network, its number of vulnerabilities, and also value. So how valuable is that host to the attacker and the defender? If there are hosts that have the same connectivity, vulnerability, and values in the networks, so what we do, we abstract it and assume it only once in the network, because it's the same, right? So assuming only one of those, it reduces the size of the problem, and we don't omit any possibilities how attacker could attack the network. So this is motivated by classrooms in a university where there are 30 machines and they run the same operating system. They actually are copies. So that's what we can do abstractly this way. And so defender, in our game, can duplicate existing host, and the duplicate would be the honeypot. So in this case, for example, defender puts 2 honeypots of type database. So here are 3 IP addresses, 2 go to honeypots, and 1 is the real database. And so we assume that attacker cannot distinguish honeypot from the real. So when he chooses one way to attack of these databases, he cannot distinguish which is honeypot, which is not. So 2 of the third times he would attack the honeypot, and 1/3 of the time the real machine. And what attacker do? He chooses what attack policy he wants to apply in order to attack the network. And so now I will focus how we generate the attack policies. So for a given network, you're familiar probably with Nessus and Mulval tools that generate attack graphs. So I will do this faster, a little bit skip. So we use Mulval to scan the whole network and generate attack graph for each network, which is like dependency graph of all vulnerabilities. And so this is the fact nodes that are initially true. These are fact nodes that are initially false, but can become true through the actions. And for those we give some rewards for the attacker. So in this case, we assume that attacker gains 1,000 unit points when he gains access to database, and 100 points for network access. And then there are the actions that correspond to exploits that attacker can attempt to perform. So each action has set of preconditions that must be true in order to perform this action, and then a set of effects that become true if action was successfully performed. And so action is defined by 4 values in our case. First value is the probability that action will interact with honeypot. So in this case, all of them are 0, because first value is 0 because there are no honeypots in this network. Second value is the probability that the exploit will end up successfully for the attacker. So this number is estimated from CVSS so far, but we would like to improve this estimation further. Then there is a cost that attacker pays in order to attempt this exploit. So it could be how long did it take for him to do this action, maybe it could be hours, or what effort does he put in order to attempt this action. And then it's just technical one, set of hosts that this action interacts with. So in this case, this action interacts with firewall. These two actions interact with the database. It's just to keep track which host did the attacker interacted with. And so adding honeypots into the network, it changes just the first value, the probability of interacting with the honeypot, and that value is proportional to the number of honeypots. It's a ratio of number of honeypots to the number of hosts in that host type. So previously I said, right, so this host type represents 3 hosts, and now adding 1 honeypot, so mean there are 3 hosts, real one, and 1 honeypot. So this action, which is done on this host, has now 1/4 chance that will be interacted on a honeypot. And so on this attack graph, we compute optimal attack policy for the attacker. So we assume that the attacker knows the attack graph so far. So it's a very naive approach so far, because in reality he doesn't know. But in this case, he knows the probabilities where are the honeypots, and also probabilities of action being performed successfully, and so on. So we translate this problem into MTP. That's finite horizon Markov decision process, MTP, and it's just a model to find a policies in probabilistic environment. So A are the states where attacker decides what action he wants to perform. So in this case, attacker can do exploit firewall, send malware, email, or create a dictionary. Each has some cost. And then there are chance nodes, which with the corresponding probability X, that it's either action ended with interacting with honeypot, succeeded, or failed. And then attacker again interacts. So this is a finite horizon tree, because he has a limited number of actions. And we compute optimal policy in the MDP. This problem is really hard, except it's actually NP hard to find optimal attack policy for the attack graph. One of the reasons is the MDP is exponentially large. And so what we seek is to find attack policy. So for example, this is optimal attack policy for the previously shown attack graph. And in this case, it recommends that attacker should first do a send malware email, and this whole attack policy has expected utility or reward 279. And if this first action attacker performs and it succeeds, so then attacker continues with the right sub policy, and if it fails, so then he continues with the left sub policy. And this is optimal in terms that it maximizes the expected reward for the attacker. So utility of the attack policy is expected reward that he obtains by using this attack policy minus expected cost that he pays for in order to perform those actions. So this attack policy has maximum utility. Okay. So I somehow missed the one slide. An attacker, defender, he put honeypots into the network, and his utility in our game is minus expected reward of the attack policy that the attacker chose, because that's what he's going to lose, whatever attacker gains as expected reward from attacking the network. So that's expected loss for the defender, and minus the costs for the honeypots. So we assume that different honeypots of different hosts has different costs for the defender. So, for example, creating honeypot of database type is much more expensive than just a workstation. So they have different costs, and also defender can choose number of honeypots he wants. So the more honeypots he puts there, the more secure the network becomes, but more he pays for those honeypots. So he needs to find the best trade-off between the securing of the network and number of honeypots applied in the network. So now I'll just present how we compute the optimal attack policy for the attacker. So we use dynamic programming. If part of the MDP, once we solve and we get to this part again via different actions, so we don't complete it once more, because we don't do the same effort twice. We use branch and bounds, those are standard technique. I will just say about the sibling class theorem, which Carlos Sarauta also used in his work. So, sibling class theorem states that in some decision point, if attacker has multiple actions that he can do, so even without exploring those actions, we can determine statistically, just based on the probability and cost, that this action will definitely not be optimal to perform in this current state. So what it does, it groups actions into two classes, OR class and AND class. I'll just explain the OR class. So if two actions have the same effect, and they are in OR relationship, meaning that if attacker performs this action, it activates this fact, so he will not perform the other action because there is no reason why would he. And vice versa, if he performs this action, he will not do this action. So therefore, these two actions are in OR relationship, and what we can do is take their actions probability to cost ratio and compute this ratio value. And so this ratio value of the action says how much probability there is per unit cost for this action. And the rational attacker will definitely not do action which has a lower ratio, the action with a lower ratio, if there is another action with higher ratio within this class. So between these two actions, the optimal attacker will definitely not do the first action. So it's simple rule, right? But it helps a lot actually in finding the optimal attack policy. Okay, so here this slide I wanted to explain. Okay, so the attacker, he chooses what attack policy he wants to do among many attack policies. He chooses the optimal that maximizes the utility. Utility is computed as expected reward minus expected cost. And defender's utility is minus expected reward for that attack graph minus cost for the honeypots. So assumptions in this game are that both players are rational. Another assumption is that attacker knows the whole attack graph and also location of the honeypots. So that's so far very naive. And also that attacker knows that if he interacts with a honeypot, so the game ends. So we assume that defender somehow will defend further on his network from that attacker by either blocking IP address, which probably doesn't work in real world, or can just let the attacker interact with the honeypot, observe him, figure out what are his goals, some his scripts get, and like somehow block him. So in our game, we assume that at this point the game ends. And so the whole game looks like this. So there is the real network of the defender. He tries all possible allocations of the honeypots. For each new network with the new honeypots there, we generate the attack graph, and from that attack graph we generate the optimal attack policy for the attacker. And so by backward propagation, we know that the defender wants to maximize his utility. So these are the outcome of the games. First value is the defender's utility, second value is the attacker's utility, and defender plays in such a way to maximize his utility. So if defender played here, attacker would choose this attack policy among all possibilities because that maximizes his utility. So here the attacker has 279, and here attacker has 70, here attacker has 52. So attacker is going to choose this attack policy. And so defender knows that if he put here, this way honeypots, this would be the outcome of the game. In this case, this would be outcome of the game, and in this case, this would be outcome of the game. So defender chooses the outcome which is maximizes his utility. In this case, it's this third one. So defender chooses to place to the right, like this honeypot allocation. So we have some A models of we ran some experiments on this network, which is like just a model, it's not a real network. So we compared the defender's utilities if he allocated the honeypots optimally compared to if he put them randomly. So it was the uniform strategy. And so this is the difference. This is the number of honeypots allocated into the network, and this is the defender's utility for the best allocation of that number. So with two honeypots, optimally the defender can gain minus 1,100, and with six honeypots, actually it was the optimal, and in this network specific, it was to put two honeypots here, probably to block the attacker at the beginning, and two honeypots were allocated to the most valuable host, which is the database. And so here are different allocations with different number of honeypots. So with one honeypot, just duplicate the server, with two honeypots, duplicate server and VPN, and so on. So we did one more interesting analysis, is that of course a defender cannot know perfectly the attack graph according to which the attacker is going to behave. So we did an experiment. So we had an original attack graph according to which the attacker behaved. However, we made it copy and perturbed a little bit the values. So we modified by 20% or 30% the values in the attack graph, and assumed that the defender has only this estimation of the attack graph. And the defender computed his best strategy according to this attack graph, and we computed what is his regret, how much did he actually worse off by not knowing the correct attack graph, but computing according to this just estimation of the attack graph. And so this was how much we perturbed the values in this estimated attack graph. So this 0 means that they were identical, so he actually computed to the original attack graph, and 1 means that this copy of the attack graph was completely random. So I assume that the attack graph would be like maybe 20, 30 or 40% off away from the original one, like the one that estimates. And we analyzed how the changes, how the defender's strategy is sensitive to the changes in the attack graph if we change different values. So first we changed only the action success probabilities in the attack graph, and it seemed to be the most sensitive to this parameter. So this is the defender's relative regret. So the higher regret the defender has, so it's like the worse for him. So it means it's very important to estimate in the attack graph the most possible precisely the probabilities. The second was the honey type values. So that was how much valuable are the host for the attacker and for the defender, and the least sensitive it was to the action costs. So that's what how much effort does the attacker put into that action in order to attempt that action. Okay, so I merged here my two works. So this was our initial work, and we now extended it in a way that attacker now does not know actually the original original network, but he has set of networks that he thinks that the company might have deployed. And so in this case we assume that attacker knows different networks that the company might have deployed, and with what probability they deployed this network. So in this case we have a network. The defender now not only duplicates existing hosts, but also can add like fully new host types, which are honeypots, and attacker chooses attack policy. So the game becomes more complicated. So in order to capture all possible networks that the network might have deployed, so we start first with a chance node, which chooses what network the company deployed with what probability. Deltas are the probabilities of deploying the network, sum to 1. Each network, the defender can extend by putting their honeypots. And what is interesting here is that, for example, for these two networks, if defender put in this network firewall as a honeypot and in this network the VPN as a honeypot, so these two states become indistinguishable for the attacker because he cannot know which is honeypot, which is real. So this creates an information set called in game theory, and it means that the attacker cannot distinguish those two states from each other. So now the attacker has to reason what's the probability that he is in this state and what's the probability that he is in this state. Meaning, what's the probability that the defender played this action and what's the probability that the defender played this action and played somehow best or optimal attack policy to those probabilities. And defender, of course, knows it, so he can exploit this uncertainty of the attacker and put the honeypots deliberately in the places which would confuse more the attacker. And so the game continues very similar to the previous one. For each network we generate attack policy, and there is a set of all attack policies that attacker can play. However, we cannot compute now exactly one optimal attack policy because so in information set, attacker must play the same action here and here because this is kind of one state for him. He cannot distinguish those, and so we have to assume all possible attack policies. And this game is exponentially large to the attack graphs, and it's really hard to solve. Actually, we weren't able to solve it optimally. We developed 3 approximation solutions. They are close to optimum, but we don't even have guarantee that it's like epsilon far from optimum. We can say how far it is at worst from optimum, but it's not epsilon optimum. It's not the approximation algorithm. It's just scalability of the actual previous work. So that's it. So we introduced a game theoretic model to model the interaction between the attacker and the defender in the network security. And here we focus only on honeypots, but actually this work is not constrained by the honeypots. There could be any actions that change somehow the attack graph. So if there would be some patches to apply or IDS or other actions that somehow change the attack graph, we can assume those in this model. Honeypots is just one that seemed cool to me, so I started to work on those. Okay, that's it. Thank you. If you have
Si alguien tiene preguntas, no la puedo armar en inglés. Alguien por ahí sí la puede armar en inglés. No va a ser yo. Pero si tienen preguntas, en inglés, por favor.
They can ask Spanish.
Yes,
Yes,
yes.
really.
I will try to.
Ahora sí, se volvió a
¿Blanco?
Why did you choose to use honeypots as the game vendors of your model?
What was the commandos?
Why did you choose honeypots as the condition that the game ends from the attacker?
Well, I understand. Why did I choose honeypots for?
The game end.
Oh, to end the game.
Yes.
Yes, to end the game.
Okay, so why he doesn't continue, right?
No,
in attacking.
Why did you choose precisely honeypots as?
Okay, so honeypot was actually this project I'm paid from is called Honey Maze. So we were investigating how, in what ways we could use the honeypots, and so we started to use it in game theoretical way, but it just, project is based on honeypots, but I don't want to restrict myself only to honeypots, so I think those could be like different defenders options beside the honeypot that modify the attack graph.
Right, because you said before that changing the probability of success of the attacker changes the most. I don't know how to put it. My question is, can you introduce another type of elements for the defender, like IDS or something like that, to modify the success of the attacker, the success of the attacker? Because I'm just not sure. Can you introduce another type of elements for the defender, like IDS, to change the attack success?
Well, yes, I think so, but then I would have to also change the attacker's attack policy. So now we assume that the attacker knows that if he interacts with honeypot, the game ends. So the optimal attack policy of the attacker is deliberately to avoid or minimize the probability of interaction with the honeypots, right? So if I put their IDS, defender can do it, it's no problem. I can actually assume it right away, so I can just think honeypot is not honeypot but IDS or something like that.
But how can, because I think like IDS in your model can act as a change, to change the attack success for the attacker. No? Like if the attacker doesn't know that there is an IDS in the network, but for the attacker has given an assumption and has the assumption that attacking certain node of the network has certain probability of success.
Mm-hmm.
But if the defender introduces an IDS, the real success of the attack is lower. How does that change for the attacker's perspective? The optimal attack graph.
So, let me rephrase it. I would introduce new action, for example, inputting the IDS, somehow that I detect the attacker. However, attacker has no knowledge that there is any IDS, right?
Yes.
So in this case, it wouldn't change the attack policy?
It wouldn't end the game, but it would change for the attacker the success of the attack. That would change anything, the attack graph for the optimal, I don't know, that would change anything.
Yes, exactly, right? So if attacker does not know, doesn't have any information where are the IDSs, or in my case honeypots,
yes.
So he has just one attack graph and he completes the attack policy and it will be always the same, right? If he has no information. So that's how. So it wouldn't change. So maybe it's actually better to somehow inform him and tell him, okay, there are like few honeypots, and actually what we hoped to find set of honeypots that the attacker would know that there are those honeypots, and he would be totally demotivated to attack because his expected reward would be the actual negative. So that we were originally aiming for. But of course, it doesn't have to work always, because if he's very motivated attacker, so despite of those honeypots, and he would try to attack, and just if he interacts with honeypot, okay, so he gets 0, right? So he always wins. Either 0 or the positive expected utility for him. Yeah, but introducing IDSs, I'm actually not totally sure how it would change the attack graph. It would probably didn't end the game, so defender would be notified that there is attack going on, but the attacker would continue an attack. And so if there would be another stage of the game where attacker can again interact somehow with the defender, could interact again somehow with the attacker to block him. If not, so then actually there's no point of notifying the administrator, right, the defender. So it would be probably a multi-stage game. So I was offered a few times that maybe I could do that, exactly the IDSs, so there would be a few IDSs, and if attacker interacts with some of them, so then assume new actions that the defender can put there. So for example, I was told restart the computer. If you know that the attacker is doing something with this computer, just restart it or just turn it off. It's still better than losing the private data. So it's a multi-stage game. I didn't do it yet, but good idea. Any other questions or suggestions?
In your model, have you considered, besides like database servers or firewalls, have you considered other kind of devices like embedded devices or like devices that could be connected to the network, but not usually mapped in that kind of network as an attack path as well?
Well, I didn't consider yet. But I can imagine how it can be extended to it as well.
And to evaluate the cost as well.
Exactly. Like for me, the most important is always the attack graph, not how it looks, the network, and so on. So if there's some if attack graph would be generated with those vulnerabilities of the embedded systems and so on, so I think it could work for that as well.
And could you implement as well honeypots that would simulate those devices as well, or you are just aiming for big servers?
Well, I'm not implementing any honeypots. I hope that some other people there out working on it, and there is actually big research on creating very real honeypots that the attacker could not distinguish, and there are like interactive honeypots that is not that if you ping it, it doesn't respond, so you know it's honeypot. But if even you hack it, it has its own system and so on. There is a research on it, so I just rely on them, and if this suggests where to put honeypots, so I just assume that there could be this type of honeypot. So also what I assume, if I have some workstation and I know it has some open ports, so I would somehow create duplicate of it, but have like random data, not real data, right? But have the same open ports, and so when he scans, hopefully he cannot distinguish. But after observing which computer, like the network flow, right? So he maybe could somehow more predict which is honeypot, which is not on the network flow. So again, that's another research for the honeypots, maybe to create some fake data. Yes.
I was before in the second part of your work, you showed us that the calculations grew exponentially, so it was more difficult to solve or to get the optimal attack. And I was thinking, maybe can you find a model where the game is a zero-sum game? For example, if the attacker has infinite money and the defender also, then it's reward versus minus reward.
So you mean the second part, this game?
Yeah.
Yeah. So we developed 3 approximations how to solve it, and actually one of them is assuming that these are zero-sum games. So good idea. And actually that approximation was very good because if it's zero-sum game, it's much easier to solve.
So you find like equilibrium because you just make the probabilities equal, right? No.
Not totally equal. You have, because
I mean, you set the probabilities for the attacker and the defender, and you find the value that
okay, you mean utility of the, yes.
Expected, I don't know.
Yeah, that's true, yes. But then you have to find a strategy for the defender, so what he is going to do where in order to achieve that equal stage.
Both strategies, right? For the defender.
Yes, but the thing is, if it's zero-sum game, for the whole game, you can write down one linear program, and that is solved polynomially, right? So that's why it's easy. If it's general sum game, it's not LP, but it's mixed integer LP, and that's NP hard to solve. So by introducing zero sum, we did 4 different ways how we can have here zero-sum game, zero-sum utilities, and that approximation was actually very close to optimum.
Okay, and could you very briefly tell us the four different ways to get a near optimal value? Because I didn't understand. One was a zero-sum game, and the other ones were?
Okay, so let me see. I have that for that presentation. It's like 3 slides or something. Okay, so what is interesting, if it's general sum game, we don't find Nash equilibrium there, because Nash equilibrium has own problems in general sum games in terms of there could be many Nash equilibria and you don't know which to choose. You may play this Nash equilibrium, but your opponent is going to play different Nash equilibrium, and then you have arbitrary big regret. And so Nash equilibrium is not good for the general sum games. And in all security games, they use a notion of strong Stackelberg equilibrium. And strong Stackelberg equilibrium is that the defender commits to a strategy. So me as the defender, I do some strategy and actually announce it to the attacker. I say with what probability I put where honeypots in my case, and attacker is going to play best response to it. And in this case, I'm always better off. I always have higher utility than any Nash equilibrium. And so we look for the strong Stackelberg equilibrium, and that's again NP hard to solve. And so using mixed integers in a program is hard. So we do one approximation. It's like the dummiest one is the perfect information. So we assume that our game doesn't have imperfect information here, but attacker knows in what state he is, and then we can use just backward induction to find the optimal strategy. Okay, so in this case, so originally attacker could have played either this and this action. That's one of his strategy, and other strategy is to play this and this, but those two actions are already bind together by cutting off the information set. So now attacker can play here best response and here best response, which was not possible in the imperfect when there was this imperfect information setting. So this was one approximation. Second was the zero sum, and so here are the 4 possibilities how we created the zero sum. One was that the defender ignores his cost for the honeypot, and attacker ignores his cost for the attack graph. So we only consider the expected rewards of the attack graph. Then
that's a zero sum game.
That's already a zero sum, yes. So this is one of the possible zero sum games, and we had 4 different possibilities how to create zero sum game. So another one was that, for example, this one's quite interesting, is that both players were motivated to play in such a way to maximize the other's cost. So defender, he minimizes his expected loss, minimizes his expected cost for the honeypot, and try to maximize the cost for the defender attacker's attack policy. And there are other things. And the last approximation, okay, so the zero sum game. The last approximation was a commitment to correlated equilibrium, but it's like more theoretical. So correlated equilibrium is where defender does not commit only to mixed strategy, but also to a signal that is going to say to attacker, okay, in this information set, play this action. It's going to give the defender only higher utility, and we tried, and from that we deducted some strategy, and it was actually very good. This one was the best of the all approximations, but it was very slow. So here are the 3 approximations. Perfect information. This was the last one, the commitment to correlated equilibrium, and this is the zero sum, ZS. So zero sum, this is how fast the runtime of each approximation. So zero sum were really good because they could solve networks with 9 types, 9 hosts, and up to 1 honeypot in that. And only perfect information and only zero-sum game approximations could solve this. The others, they stuck here, for example. The green one stuck here. The commitment to correlated equilibrium stuck here. It couldn't scale further. And this is the regret. So commitment to correlated equilibrium was the best, has the lowest regret. Then there was the single oracle general sum, and here the zero-sum games. And here was the perfect information. It was the highest regret. So it's pretty bad actually, because then defender cannot exploit the information that attacker does not know where he is. So I would play in order to confuse him, and the remaining could.
Sorry, I have a question. How do you deal with the fact that there can be multiple entry points to an endpoint?
So we assume here that there is an internet entry point, right?
Yeah.
But each host has 3 types of vulnerabilities: local, remote, and client. And so the remote vulnerabilities means that this host can be directly attacked from the internet. And so we just add it as a new vulnerability, and then I don't deal with it. Mulval generates me its attack graph, and I just solve the attack graph. So yes, good point is that I should model the network as real as precisely in order to get real attack graphs. Okay, if no other questions, so thank you for listening.